Welcome to this Calculus 2 podcast. In today's podcast, what we're going to be looking at is another review topic, specifically L'Hopital's rule from Cal 1. So let me just start off by reminding you what L'Hopital's rule is, and then we'll do an example sort of highlighting the way to use the rule. The easiest way to think of the rule is that when you're taking the limit as x approaches a value of a ratio of two functions, so we'll call them f of x and g of x, that you can replace the functions that you're working with, and instead of taking the limit as x goes to a of the functions, take the limit as x goes to a of the derivatives instead. Now it would be nice if we could just stop there and say that's L'Hopital's rule, but honestly when you work with L'Hopital's rule there's several other little bits and pieces that you have to keep in mind. This doesn't work for any f and g, and it doesn't necessarily work for all values of a with f and g. So there are a couple of little caveats here. The first is that we need to know that the limit as x goes to a of f of x equals the limit as x goes to a of g of x, and that both of these limits are 0. If that's the case, then what we call this is a type 0,0 indeterminacy. So remember, these are what we call our indeterminate forms. You could have that type of indeterminate form, or you could be dealing with the limit as x goes to a of f of x equals the limit as x goes to a of g of x, and those limits are plus or minus infinity. Now it's probably not kosher to use equal here when this one could be negative and this one could be positive, but they're both infinite limits. In that case, we say that this is type infinity over infinity indeterminacy. Now, this is an either or, so f and g either have type 0,0 or type infinity over infinity, and in either case, 1 or 2, we can have following restrictions on a. This also applies, in other words, 1 and 2 also apply for values of x approaching plus or minus infinity, or one-sided limits approaching a from the right or approaching a from the left. So you can mix and match any of these conditions in 3 with 1 and 2 and apply them to L'Hopital's rule. But, let's kind of bring this back for a second. What we really mean when we say L'Hopital's rule is we mean this process here of replacing the quotient of two functions with the derivative of the quotients. Now, there are other types of indeterminacies. And rather than make a video for each of these, what I'll say is that they are handled in much the same way that the type 0,0 and type infinity are handled, except that you usually have to use some sort of property of logs or something else to get them in the right form. These indeterminate types are the 1 infinity type. Now this is 1 raised to an infinite power. So the base is heading toward 1 and the power is heading toward infinity. Here, this is a 0 raised to the 0 type and an infinity raised to the 0 type. You also have indeterminate forms 0 times infinity and infinity minus infinity. If you ever encounter these forms in a limit, you can't tell me what the answer is. Excuse me. One of the most common mistakes that students will make is they'll say 0 times infinity is 0 and infinity minus infinity is 0. And in fact, that's not necessarily the case. All of these can be handled with L'Hopital's rule if you can get the resulting equation in the right form. And sometimes that's trickier than I'm making it sound. All right, let's look at an example. And I've picked sort of a special example here in the sense that we're going to get to do L'Hopital's rule more than once. So let's start off by looking for the limit as x goes to 0 of e to the x minus 1 in the numerator and x squared in the denominator. This is sort of a classic L'Hopital's rule problem. If you're reading through any of your textbooks, chances are you'll probably run into something very similar to this. So let's go ahead and evaluate the numerator and denominator separately. Let's start off the numerator first. What we're trying to do is we're trying to see what type of indeterminacy we have. We're testing either for condition 1 or condition 2. And so the limit as x goes to 0 of the numerator is going to yield the following. Just simply plug in x equal to 0 where you see it. And in this case, we get 1 minus 1 or 0. So we know that the numerator is type 0. How about the denominator? Well, the denominator is fairly easy to calculate its limit of. It's simply just 0. So because we have 0 in both locations, this is the condition 1. This is a type 0, 0 indeterminacy, which means that we can apply L'Hopital's rule. All right, in applying L'Hopital's rules, we get started here. Let's just go ahead and rewrite our limit. So this is our original limit we're looking for. And then what I like to do is if I'm doing a L'Hopital's rule step, I usually like to indicate it over the equal sign by just writing LH. So that tells the grader or anybody that's reading your work, hey, I'm applying L'Hopital's rule here from step 1 to step 2. All right, so this is now the limit as x goes to 0 of, and I can replace the numerator and denominator both with their derivatives. That's what the L'Hopital's rule here in the red box, that's what it tells us to do. So the derivative of e to the x is e to the x, the derivative of negative x is negative 1, and the derivative of negative 1 is 0. On the bottom, the derivative of x squared is 2x. And so here's the new ratio that L'Hopital's rule wants us to look at. So I need to also go back and check for indeterminacies here. Can I simply apply the limit at this point? If I was to try to apply it in the top, I'd get e to the 0 minus 1, which is 0. If I tried to apply it in the bottom, I'd get 2 times 0, which is 0. I still wind up with a 0, 0 indeterminacy, so I can't say that the limit is anything at this point. What I can do is I can go back to L'Hopital's. Yes, we're doing L'Hopital's a second time. That's perfectly valid. We could have just as easily have started with this one, and then we would have done L'Hopital's knowing nothing about the previous quotient that we were given. All right, here let's look at the limit as x goes to 0 now of, let's apply L'Hopital's again. So the derivative of e to the x is e to the x, and the derivative of this minus 1, this pesky minus 1 that's been haunting us on both the previous problems, that now goes away. And then if you're looking in the bottom, the derivative of the bottom is simply 2. If we then apply our limit, the limit as x goes to 0, well, this is e to the 0 in the top. There is no x in the bottom, so it just stays 2. And e to the 0 is 1, and so we get 1/2 for our answer. This is, in fact, the solution for this particular problem. Now, L'Hopital's rule is extremely valuable in understanding which functions grow faster than other functions. You can compare their ratios by comparing their growth rates. Growth rates, remember, are derivatives. So it makes a lot of sense that this is a very easy to apply limit technique, but it also kind of ties back into the idea of the derivative as the rate of change. And that's going to be an important concept as we go forward in Calculus 2, especially when we start looking at things like indefinite integrals and the integral comparison tests later on with series. This is stuff that you're going to need to remember from Cal 1. All right, thank you for viewing this podcast.